the issue of performing science related to the human exploration program, and certainly its interaction with robotic programs. We're going to hear 4 briefings on this, different aspects of sciences. The first will concern the biological and physical sciences, and our briefer will be Elizabeth Cantwell. Thank you very much for joining us.
Good morning. Thank you very much for having me. It's a bit daunting to go after Bob Zubrin. I cannot bring the level of zest that he does to the table, so I'll just ratchet down a little bit. But I always appreciate when you speak. I've seen you many times, Bob. As Mr. Augustine said, my name is Betsy Cantwell. Several of you on the committee have some familiarity with me. I welcome this chance to discuss my experiences and perspectives on life and physical sciences in low-gravity environments. I've been a researcher for many years in this area, a research manager, and perhaps for an even longer time, a critiquer in the form of many National Academy reports in this area. I'm currently the co-chair of the National Academy of Sciences Decadal study on this subject. My co-chair is Wendy Court from the University of Colorado. And as this study has just kicked off, I will not have a lot to report on our findings. I will have a couple of slides where I discuss our approach, but I do have a long career and a long association with this research area, and I'll use my own background and discussions with colleagues to give you what I hope is a useful perspective. Next slide, please. This is very much in my face. A decadal study typically develops a set of priority research topics for NASA and options for implementation plans for future missions. The NASA has commissioned decadal studies. Oops, now I have to have it in my face. I didn't like that, but I'll do it for you. NASA's commissioned decadal studies a number of times over the year, and you'll hear from my colleagues after me. This is somewhat unusual. It was requested by Congress to focus on a greater understanding of life and physical sciences phenomena in reduced gravity environments. The objectives are fairly common for a decadal study, but let me point out that NASA has asked the National Academy to focus on research areas that enable exploration missions and are enabled by exploration missions. And as a committee, we've assiduously tried to keep our focus on the future and the value that a research portfolio in these areas can bring. I will discuss this research portfolio in the context of both enabled and enabling, but I'm going to focus on enabling. You'll see that they're hardly mutually exclusive. On the bottom of this chart, let me just point out there's a little graphic that outlines the connection between life and physical sciences in low-gravity environments, which is both some commonality and relevant phenomenology, and I'll give you a little bit of a discussion about that, and exploration requirements. I'll also discuss that. And the steering committee for this decadal study has discussed the commonality elements between enabled and enabling. And you'll see as I talk that there are a number of commonalities. There's obvious links between the two, but the key link that I'd ask you to pay attention to is the need for common infrastructure for research laboratories in low and microgravity environments. I understand there's been a great deal of discussion so far in both public and private committee meetings regarding the ISS. I have a place at the end of this talk for a little bit of a discussion about that. Next slide, please. So my last slide on our decadal study, let me tell you about the 7 subcommittees that we're in the process of populating with experts. They will cover the basic areas of expertise most relevant to life and physical sciences in reduced gravity environments. The country has some history in this area. We also have a strong sense of the need to address translational research as systems elements of both human spacefarers and spacefaring hardware are such an important potential endpoint for research in this area. The bottom line is that there's an incredibly broad suite of research areas bound tightly by infrastructure and systems applications. Next slide, please. Let me start with a short discussion that can be of science that can be enabled by access to reduced gravity environments. I'd like to point out as I begin that there's a history of research programs in all of these areas that I'll discuss today. Most of the research that in these areas that might have focused on reduced gravity environments over the last decade has been reduced in cost by about an order of magnitude, or in budget. I'm not actually going to discuss that. I'm happy to answer questions, but I'd like to point out that we've had at various times in the history of this country various sizes of research programs in this area. It's down around $50 million at the moment. I'd be happy to field other questions, as I said later. In the life sciences, studies in things like mechanobiology, topics like cellular mechanotransduction, these are areas where the absence of the ubiquitous terrestrial mechanism of gravity will often yield new results. Similarly, gravitational effects, gravity affects behavior such as gravitropism, and this is something that can be uniquely studied in a low-gravity environment. I'd like to point out that as we have reduced our funding and studies in this area, both the Europeans and the Japanese, the international community in this area is very robust at the moment. Also in physical sciences, there's a number of areas where gravity, while not inducing an effect, can mask it substantially in a terrestrial environment. So investigations in phase transitions, for instance, are uniquely able to produce new results in a low-gravity environment. And in combustion physics, looking at surface reactions or soot dynamics, in the absence of convection, can and has elucidated mechanisms that have not been seen and are very difficult to see in a terrestrial environment. Next slide, please. As a start to research that enables exploration, I'm showing you here some elements of human and exploration systems that are relevant for life in physical sciences. There are risks, and I've outlined some risks here, and I've shown you mostly risks for humans. There are also clearly risks for hardware systems. There are also system functions. There are a host of requirements associated with expanding our abilities to explore in space. And there are numerous gravity-dependent phenomena that are imperfectly understood and play a role in all of these areas. Next slide, please. This is a busy slide, and I'm not going to cover every word, but I wanted to give you a sense of where scientific investigations can, and in many cases must, play a role in some of the challenges associated with human exploration. What you see here is a graphic of two of the exploration scenarios, and there are many more. I know you all are well aware of all of them, with a representation of the elements of exploration challenges that can be addressed with research in life and physical sciences, research in low gravity. You'll notice that there are competencies such as radiation, various elements of materials development or materials understanding, and multi-phase flow that show up all over the place. There are a number of key research areas that must make a contribution across the board to solving these challenges. Next slide, please. Okay, this slide is a very small selection of areas from across this research portfolio where there are links to terrestrial challenges. I show you this not because I'm interested in demonstrating dual use. My intention is to show that the plethora of science commonalities across exploration and terrestrial challenges do exist. There are absolute science commonalities. Translation of these scientific endeavors to meet either an exploration challenge or a terrestrial challenge would represent an entirely different set of considerations. In other words, it takes a different set of considerations to translate a science endeavor to a terrestrial challenge, such as meeting our current energy portfolio needs, or an exploration challenge, such as aerospace energy or power. Next slide, please. Onto research platforms. All of these modalities that you see here, which is everything from drop towers, where you can get about 10 seconds of low gravity, to the ISS, or something that doesn't exist today, planetary laboratories, where there's a continuous access to the reduced gravity environment that we'd be interested in, are useful. But it is ISS and something like a planetary laboratory concept that hold the most promise of utility because of the continuous availability of a low-gravity environment. So let me give you briefly the perspective of my science community on the ISS. Right now, it is the only scientific laboratory we have that makes low gravity continuously available. It's all we've got. Though we have hardly, in my decadal study, begun looking at an integrated analysis of research that we would like to see done, I can tell you that there's a great deal of important work that can be done on ISS. And if you're, while we have not produced our results yet, there's a very useful ESA study that's on the street from September 2008, looking at their integrated life and physical sciences portfolio. And I recommend that to you. We, the Europeans and the Japanese, all have emplaced experimental capabilities to do life and physical sciences research on ISS. And we finally have the ability to have 6 crew members on board, which allows us a lot more opportunity to utilize those capabilities. Let me just point out that, at least from the perspective of my science community, in the life sciences, there's a lot that can still be done on ISS to reduce human health risks. Most importantly, bone and muscle. There are immunological studies that are very important to be done, cardiovascular, and of course, looking at the risks of radiation and how to mitigate those. And on the physical sciences, and these are really perhaps focused on fundamental research, but that can directly impact and help almost any exploration future you can predict. Cryogenic fluid mixing, multi-phase flows, which is an incredibly difficult problem, which we do not understand at the levels that we need to understand it, and all kinds of heat transfer issues. And the last slide, please. So this is essentially, the slide is just a distillation of everything I've talked about. I wanted to make sure that I had plenty of time to answer questions if you have them about this portfolio. I apologize for not being able to go in greater detail about the considerations of this particular study, but we have just begun. We have a really remarkable group of people who have signed up, approximately 60 or 70 people who have signed up. I have a 19-person steering committee, and I will tell you that many of them have come to the table once again to provide recommendations because they really believe in doing this kind of work, even though many of them have over the years seen their work funded at lower and lower and lower levels. So thank you.
Thank you very much. We do have time for questions, so Chris, you want to start out?
Thank you. Thanks very much for that presentation. At our last meeting in Cocoa Beach, we talked about a candidate set of figures of merit that we would apply to all the scenarios that the committee's going to consider, and one of those figures of merit is going to be scientific. It's science, value for science. Not that that's necessarily the driver, but it's clearly an important figure of merit. So what I'd like to do is try to, based on your presentation, to try to draw some conclusions within this domain at least for how we might try to scale different scenarios. And it seemed to me, but don't let me put words in your mouth, that's why I'm asking the question, that the most directly relevant comment you made, or maybe the most important comment you made in that respect, was your comment that the International Space Station and planetary laboratory access hold the most utility because of, and planetary laboratories hold the most utility because of continuous access.
Yes.
Would it be right then for us to take from that scenarios which establish, which either keep the ISS flying for some time or establish a long-term lunar base or Mars base are the most interesting from the point of view of your science because of that continuous access to lower microgravity, and scenarios that don't establish those kind of bases are less favored? Or if that's not right, tell me what's right.
No, that's correct. Certainly, and let's talk about less favored for a moment. You just can't get as much, and we're talking about a science portfolio that is focused on producing results that allow us to make really valid scientific statements. You've got to have continuous access to experimental facilities that give you the time on target so that you can get enough data to make whatever statistical inferences you need to make. Science typically requires access to scientific facilities for not just once, but for enough time, and that can be perhaps in however many shots you get of a large laser, for instance, or continuous access. Either way you look at it, it has to be a lot of time on target. And in this case, that's time in the relevant environment.
I'd like to follow up with a question,
Yes.
if I could. Appreciate the need for time on target, but could you also share your perspective on the relative value of robotic experimentation as well as, clearly there's a need for human exposure here in order to get the proof in the pudding, but have you made any assessments about what the opportunities might be for robotic excursions that may be valuable?
So certainly as a committee, we have not had that discussion. So any comments that I make are really personal comments. And my personal experience says that there are times when one could envision creating an autonomously operated laboratory. However, my personal experience is that when you really do top quality science in an autonomous manner, it is extremely expensive. And it may not cost less than having a human there to do it. Yes.
Please, Jeff.
I've been getting a lot of correspondence from people suggesting to me that there's a factor that we haven't talked about, which is if you're going to get good scientific utilization of the ISS, it's not just a question of how much mass you get up and down from it, but a question of how frequently you can do so. That we could do a lot more good science up there if you could discover things and send new things up or bring samples back with greater frequency and time. I'd like to hear your comment on that.
Well, again, personal comment, but that's almost common sense. The question is, how much additional value could we actually bring in the time, whatever that time is, that we have left to utilize station? And I didn't make a very clear comment, but let me say that those kinds of considerations really ought to, for this science, this is an international science community, and it's clear that there's a lot of international capability on the station. Those kinds of discussions should be held with the entire international community.
Please. Leo, Merrick.
I just have a quick question about interest in the community. Of course, there are a lot of core of scientists that are very much interested in continuing microgravity or other research in space. But a lot of them have been burned over the years, and you kind of alluded to that. My question is, if access became more regular, perhaps through commercial means, do you think that there would be a resurgence in interest, or would there be wariness in coming back? And particularly in perhaps commercial ventures, like perhaps pharmaceutical companies.
I think well, again, this is a personal comment. I think you'll see both. There are members of the community, significant members of the large numbers, and very well-known people who've been burned in the sense that funding for these, the way you build a science community is not just money, but it is associated with the amount of dollars and the length of time. You need to guarantee people that they're going to be able to get funding to do this type of work for long enough to make substantial, what scientists live for, to make substantial findings within their community. However, there's also, I think there's a chance to rebuild this community. And as it was built 15 years ago, which is with a real assiduous focus on bringing young people into the community, everybody's going to watch and see were this to be funded at any level again as to whether or not the United States in particular was serious. It's clear that the European community and the Japanese community have been serious. They have their funding levels have gone up and down somewhat, but they have maintained a community. We have not really done that. However, I don't see any reason why you couldn't do that in the future, through a number of ways, and commercial is clearly one of them. Yes.
Well, thank you very much for your comments. We're very appreciative of your time.